All right, so a big part of this class is really just understanding a mathematical model, which means you really want a good definition for what a mathematical model is, what you can do with it. Uh, the simple definition for this is it's really an equation or a set of equations that describe some sort of real world situation or phenomenon. Um, and they don't even have to be a complicated equation is the really cool part. They just have to be an equation that's set up to describe something that actually exists. Oftentimes they'll take the form of like some sort of function equal to zero. The equal to zero part isn't really a special part. That doesn't necessarily make it a mathematical model. Again, what makes it a mathematical model is it's describing something real. Here are a couple of quick examples to kind of wrap your head around what I mean by these models. Maybe I'm trying to describe how the sides of a right triangle are connected to each other. And of course, we have a really good relationship for that. We have the Pythagorean theorem. If I want to shift everything over to one side and get it equal to zero, I can. This would essentially be my function set equal to zero. And it would be my mathematical model that I could use. Here's another model. This represents the weight of a rock. Maybe it's a very good model. Maybe it's not a very good model. I don't know. But either way, again, I could kind of shift everything over to one side, and then I'd have a function equals to zero. Let's see, what's what's a good example for other models? I saw one when I was going through various different notes that said something like time is equal to money. Maybe I'm trying to describe what time and money are worth, and this is my particular model. It may not be a very good model, maybe there's not a very good connection between time and money or how those two things are, but it is, some sort of equation that I'm using to describe the world around me. I could play around with it and maybe come up with better models. Now, one of the things that we're often interested when it comes to these models is really making sure that they make sense. And that not only includes being a fairly accurate representation, but also making sure that the units involved are kind of balanced out on both sides of the equal sign. We call this idea of really balancing out those units dimensional homogeneity. It essentially stands for, keeping those dimensions, keeping those units the same on both sides of the equal sign. You may also know this by another name. Sometimes this will be called dimensional analysis. Either way, those are just fancy terms of saying, hey, yeah, make sure the units match up. Let's look at some quick examples to maybe see what this is even talking about, right? So here I have just a couple of examples. This one is dealing with mass, which is equal to density times volume. And we might be interested in trying to figure out, okay, what units would we need to have in here to make sure that is dimensionally homogeneous? So we might look at the units for each of these things. So I know that mass is measured in kilograms. The density of something, that is our kilograms per cubic meter. And then the volume, I can measure that in cubic meters. So we can see that all of the units are balancing out here. The cubic meters would cancel out with the other cubic meters. I'd have kilograms equal to kilograms. Yes, this would be dimensionally homogeneous. Sorry about that. All right, let's try another one of these. This one is mass equals concentration times flow rate times time. Again, is this balanced? Is this not balanced? I don't know. Let's figure it out. So mass, maybe we'll measure this in, let's see, milligrams. We have a concentration, which would be in milligrams per liter. A flow, let's say these are in liters per minute or liters per hour, some sort of flow rate. And we'll do time also measured in minutes. All right, so I need an equal sign in here. Let's see what cancels out, what gets to survive here. So liters are gone, minutes are gone, milligrams equals to milligrams. Yeah, this one balances out. This would be a good example of something that is homogeneous in terms of its units. Now, of course, I'm kind of putting in the units to make sure that these actually do work out, that they are nice and homogeneous. We could, let's say we decided to measure the, I don't know, how could we make something that was not homogeneous? If we did the flow rate in something like liters per hour, but then we were measuring the time in minutes, that would be a little bit of a problem. Then the units wouldn't cancel out. They wouldn't balance on both sides. Oftentimes you'll see problems like this. They'll give you an equation and they'll want to know, what units should be associated with a certain variable in order to make things dimensionally homogeneous. In fact, let's look at a quick example, see exactly what I'm talking about. So this would be the ideal gas law. And we have the various different variables in here, like PV is equal to nRT. And you can see what all of these represent, and of course the units for each of these. Okay, I'll give you a few seconds to just kind of read it over. Our goal with this one is to really figure out what units should go on R to make this thing dimensionally homogeneous. So, we want those units to balance out, right? But how are they going to balance out? All right, so let's see how we can go through this process. I'm first going to take the equation as it is. And I want to get a good sense of the variable that we don't know its units right now. So this is the one where we're trying to determine the units on R. So I'm essentially looking at that, and I'm going to solve for R in the equation. All right, no worries. R is being multiplied by n, and it's being multiplied by t. So if I want to kind of move those off to the other side, I can divide by both those variables, and they'll show up on the left. All right, perfect. Now, I've been playing around with these different variables, but now we can go ahead and put the units into all of this to see what the units on R really should be. All right, so let's see, how are things measured here? Let me grab my highlighter. So let's start off with P. Looks like we have atmospheric units, so ATM. What do we got for V? V is measured in L. N is measured in moles. And T looks like we are in Kelvin. Perfect. So what units really need to be on R? Well, it looks like we have ATM times L divided by moles times K. Those are the proper units to make this thing homogeneous. Now, the cool part about this is you can really take the original equation, you can take these new units for R, and actually just check to make sure it all works out. So I'm going to write down that ideal gas law one more time. So that's PV equals nRT. And now just go ahead and write the units for each of these and double check to see what's going on with these. All right, so let's start off with P. What do we say? Those were our atmospheric units. V, that was our volume. So we got our liters. N, we got our moles. Temperature in Kelvin, okay. So in for R, we need to put our units that we just discovered. So let's see, ATM times L moles times K, all right. And now we have to check that things actually balance out. So I'm seeing that the Ks are going to cancel, moles are going to cancel. Sure enough, we have ATM times L is equal to ATM times L. Things are balancing out. We know that these really are the proper units for the variable R. Does that make sense? Excellent, excellent. Oh, I see a question that just popped up that says, will these recordings be posted somewhere so that we can watch them later? With our midterm prep and our final exam prep, usually we do have recordings available that you can kind of watch at your leisure. With our weekly preps, we actually don't release those recordings, which means if you want to participate, if you want to view these, you pretty much have to be there when we're doing these live. So yeah, unfortunately, the recordings for the weeklies are not posted. All right, good deal. Any other thoughts or questions before we move on? One word of advice then before we move on to the next one is really kind of look at the world around you and think of trying to develop your own models. Remember, these don't have to be complicated, they don't have to be fancy, but it's kind of a fun exercise to just kind of get in the habit of really connecting the real world to some sort of equation, and it can be a lot of fun. Sometimes it's a lot of fun actually collecting data to try and see what you can come up with. All right, let's talk about relationships between quantities. This will really help you as you're building those models as kind of a fun exercise. So there's two types of scalings that you want to be aware of when it comes to these various different models. You have isometric scaling and you have allometric scaling. And both of these are associated with their own little equation. So first one for isometric scaling, essentially what we're happening here between both of our quantities is that they are growing proportionally to one another. And the equation itself is really just the equation of a line. So you're seeing, maybe a good example of this would be like y equals 3x. And it's really telling us that, for every x value, if I multiply that by 3, it'll give me a value of y. In allometric scaling, the two quantities, they actually grow disproportionately to one another. So it almost looks like a very similar equation. But what you're noticing is that there's some sort of power associated with that x quantity or with the input quantity. So that's going to create things growing disproportionately because for every x that I put in there, it's going to first get multiplied by some sort of power. Think of an example like y equals, let's use that 3 again. I already used it once, but why not? Maybe I'll do something like x to the 4th. So now when I put an x in there, it's going to get multiplied to the 4th power. It's going to grow quite quickly, and then it's going to get hit by 3. This is a little bit easier to see if you actually look at the graphs of these two things. All right, so let's look at this example here. On the left side, I have some isometric scaling. On the right side, we have some allometric scaling. And if something is growing in proportional to one another, you essentially get your data that essentially looks very linear. As one quantity grows, the other quantity is going to grow. And it's only different by some sort of constant. So that's why you get that nice straight line featuring here. Of course, when working with real data, it's going to be slightly off that line. It's not going to be exactly linear, but in general, you will get this wonderful, nice linear shape. Now, not everything in the real world is linear. Sometimes you get these relationships where maybe they start off and it looks almost linear, but then they start to grow extremely fast. In fact, a lot of your data will probably be grouped up near the bottom here, but then it has this feature where it really starts growing very, very quickly. And that's usually a telltale sign that that one of your variables like x is being really raised to a power. That's where you're getting that allometric scaling. Good question. Is it always going to be exponential? The answer is yes. Since that power is not going to be 1, you will get that nice exponential growth on there. Now here would be a good example of actual taking some data and getting a good sense of why we'd want to identify something like this. So when you're looking at allometric graphs or anything like that, they can be very difficult to read. I mean, look at this. A lot of our data, it looks almost flat near the bottom just because there's not a whole lot of growth going on initially. But then all of a sudden, and this one it just happens to be, somewhere around 2009, that's where it really starts to grow very quickly. And it's hard to kind of differentiate what's going on earlier with our data versus a little bit later with our data. So if we can identify situations like that, then we have a better chance of, let's say, modeling them and maybe even transforming them into something that actually looks more linear. All right, so what's the secret for doing this? If we want to take some of those allometric models and be able to analyze them a little bit better, well, the answer for this is to get really, really good at logarithms. You can essentially rewrite this type of equation using your rules of logarithms and turn it into something that is actually linear. And essentially you use two very important logarithm rules in order to get this job done. Let me write these down. These will be really good for reference. One of these logarithm laws that is very useful is dealing with the logarithm of things being multiplied inside of that log. Actually, I need just a little bit more room. Maybe I'll write it over here. So if I'm dealing with something like the natural log of a times b, according to the rules of logarithms, I can split this up into the natural log of A plus the natural log of B. So one of our rules just really allows us to kind of split things up into addition. The other rule that is very handy for taking care of these allometric scaling problems has to deal with powers inside of that logarithm. This rule says you can take that power and move it out front as a constant that is being multiplied. All right, so we can take both of these individual logarithmic rules and just apply them to our equation and get something that is going to be linear. So I'm going to just rewrite this equation here, y equals b x to the n, and then we'll start to play around with it a little bit. Good question. This question says, if you aren't given a graph, how do you really know to transform them using the natural log? I do have some examples a little bit later on. You'll see that they usually give you a clue in the way they ask the question itself. They'll give you a clue that you should be applying a natural log to those. But excellent question. Yeah. Yeah, we'll take a look at those in just a little bit. All right, so here we have our equation. It's definitely got that exponential part, x to the n power. And I'm going to take the natural log of both sides of this. So I'm taking the natural log of the left side, natural log of the right side. And of course, on the right side, there's where you really start applying those different rules of logarithms. So looks like things are being multiplied. I have a b multiplied by an x to the n power. And I'm going to split that up into two different logarithms. My rules will say that these will be added. So that's the natural log of x to the m. I'm just going to write that as natural log of y on the other side. Nothing really crazy going over there. And then I can see in that last logarithm, x is being raised to the power of m. So I can bring that m out front of my logarithm, and it will also be multiplied. So natural log of y equals, let's see, we got our natural log of b, plus then we have our natural log. We're bringing that m right out front. We'll do that in green. M right out front, good deal. X. Now I said that this essentially is going to turn it into a line, but if you look at it at first glance, of course, it doesn't look like much of a line. It looks like kind of a mess with a lot of those logarithms in there. Let's translate exactly what we got going on here, see where that line is hiding. So there is a line in here, but you get it from really renaming things. So instead of really calling your variable y, maybe we'll call this y star. Instead of the natural log of b, I'm going to call this b star. So m is our slope, and here I'm going to call this x star. So through a renaming convention, essentially you do have a nice linear line. My new input would be x star. It has a slope associated with it. That would be the m right next to it. A y-intercept at b star. And then the associated output, or the y values, would be that y star. Let's go ahead and label those. Slope. We'll put that as y-intercept. Good question. This one says, what exactly does the little star mean? I'm just renaming things. So if you wanted to write each of these out, so y star is really just my new name that I'm giving for the natural log of y. And this is done to really show that we have a pattern going on here. So if I want to take my original equation and do some new scaling for it so that it looks more linear, I'd go through this algebra, I can apply these natural logs, but in my new graph, what I'd probably be graphing is x star versus y star rather than the original x versus y. Actually, that's a really good segue to where we're actually going with this. Once you've gone through all of this work, you have essentially brand new variables. Then you can take your graph and now graph it in what is known as log-log space. Any questions on any of the math so far, though? Excellent. All right, so let's take a look at exactly what this does for us in terms of graphs. Why would we want to do this? Well, by using logarithms on our equation, we essentially take the original points and we can now take them into a brand new space where we're looking at the logarithm of those new points. And this is what we call our log-log space. So yeah, in a nutshell, we're taking our xy points, we're turning them into the natural log of x and the natural log of y. If you have something that is isometric, so it's already linear in a sense, it's not really going to change a whole lot. It's going to take a line and it's just going to turn into a different version of a line. So it doesn't necessarily help too much with those situations. I mean, it will take our original slope. So the original slope was a slope of b. And you will get a new slope out of this that has, let's say, a slope of 1. Keep in mind that these are not the same variables. This is what I'm calling x star, and this is what I'm calling y star. And really what it's taking the slope, or what it's doing with that slope, is it's kind of getting shuffled into the brand new y-intercept, or the y star intercept. But again, for something that's isometric, you're going to get a line after going through this natural log process. Excellent. Now let's see what happens with something that's allometric. This is really where it shines a little bit more. So again, you can kind of see there's that data. It's maybe kind of grouped there at the bottom, but then it starts to take off. It has kind of an exponential look to it for sure. Yeah, we're dealing with something like x to the m power. But after going through this work, you can see there's our brand new equation and it turns it into a line. So all of this data that was kind of like crunched up at the very beginning was very kind of difficult to differentiate from each other. It's going to end up somewhere on here on the line and we'll be able to better pick them out. Let's go ahead and label what we got going on here. So here's our natural log of y. That's what we're calling as y star. The power that used to be on x, that's actually going to turn into our slope. So then I have the natural log of x, that's what we're calling x star. And natural log of b, that is going to be our new y-intercept. Good question. This one says, will we be asked to convert into log-log space? And if we need to do some log-log space stuff, how do we know they mean natural log versus an actual just regular, let's say base 10 log? You know, how do we really know? Well, I'll say most of the time you like to use the natural log. Really what we're taking advantage of here is really those laws of logarithms. We're using the laws of logarithms to kind of bring things out of the power. So in which case, in a weird sense, it actually doesn't matter if you use a base 10 log versus a natural log. I would stick with the natural log just because it is more common, you know? All right, that brings us to a wonderful question though. How do questions look like this? What are they going to ask and what can we do with them? All right, so let's go ahead and talk about models, play around with one, see what we can do. So imagine that we have two different things we're trying to model. I'm trying to model happiness and motivation. Both happiness and motivation, I'm going to say, are connected to some sort of mystery factor A. So here initially is my first model for happiness, and then I have another model for motivation. I'm not really sure what A is. Maybe it's based off of how many lollipops I get in a day. Who knows? It's based off of some A factor. Again, don't necessarily think of these as very accurate models or very fancy models. They're just something that's trying to describe some sort of phenomenon, happiness and motivation. Let's see what we can do with these. With these models, we want to determine what happens if we double the value of A, our mystery parameter. What does that do with happiness? What happens? So we want to think of what our current model does, and then since it's associated with an equation, we can play around with that equation to see kind of a hypothetical result of doubling that A value. Let's give it a try. So I need to grab our model for happiness, right? So this is our current model, has some sort of mystery A parameter, looks pretty good. But we want to answer, like, what happens if we actually double this mystery parameter A? Well, the advantage of having an actual equation as a model, it's very quantitative, is we can actually put in some more additional numbers. So if I double A, I can put that into the equation and see what happens. So let's really highlight what we've done. I'm really just replacing the A with a 2A, and then we're going to track those changes in the equation. All right, let's see what we got. So let's see, if I take 2 and I raise it to the power of 4, I can also take A and raise that to the power of 4. Now, some of these pieces are really the same pieces that were in my original equation. So I'm really just going to take those pieces that were originally there, kind of rewrite them. So those are 3 multiplied by the a to the 4th power. And with this 2 here, I'm just going to write it out front, just to kind of highlight that that's really the only piece that's different from my original. So let's see, what is 2 to the 4th power? That'd be 2 times 2 times 2 times 2. That'd be a 16. Excellent. So, by having this nice equation associated with this phenomenon, now we can quantitatively say what's happening as we change things. So if we double our mystery parameter A, it looks like we get 16 times the happiness, or that it goes up by 16. That's the only change we have from our original. All right, thoughts or questions on that example? Excellent, excellent. Once you've seen the process once, it's a good time to go ahead and try it for yourself. Go ahead and try part B on your own. This one says we're going to take the value of A, but this time we're going to chop it in half. We only want half the amount of A. What does that do for our motivation? Yes, it's going to go down if we decrease A, but the big question is how much? Maybe I'll leave the rest of this. Yeah, I can kind of see the rest of it. Kind of use our part A as a guide. If you have something, if you have a number, go ahead and type it in the chat box when you get it. That way we can kind of compare what we have and really go from there. Excellent. Yes, yes. Looks like you are on the right track. You would essentially have to multiply by 1/4, or you could say that the motivation is going to decrease by a factor of 4. Those would be great ways of saying it. Let's go ahead and go through the math. So that way, if you didn't get that 4, where does it come from? We want to be on the same page, right? So this one involves our motivation model. So I'd really start with that one. So motivation is based on some sort of mystery parameter. Let's see, and what is that equation? I think it's 1/2 multiplied by A squared. So like before, we're kind of answering a question. We're using this model to see what happens if we take the value of A and just chop it in half. So we are going to substitute that in there. So 1/2 A, and that gets squared. Right now we'd go through a little bit of algebra, not a whole lot. Square 1/2, that's where the 1/4 comes in. A is still being squared. And then this 1/4 is really the only piece that is different from our original model. But if you want to make it extra clear, then you can go ahead and just kind of shuffle things around so that the 1/4 is out front. And then everything else is written after that, because the order of multiplication doesn't really matter. So yeah, you can see that motivation is going to decrease by a factor of 4. You can say it's getting multiplied by 1/4. Exactly right. Very nice job. Right, on to other questions. What kind of relationship is this really? Is it going to be isometric or allometric? What do you think is going on? Specifically, we're talking about the relationship between H and A. Again, if you have a guess and you want to type it in the chat box, go ahead and do that now. Excellent. Yes, I would agree. This is definitely allometric. And of course, you can see this in a couple of different ways. If you're looking at the equation, it has an exponent that's not equal to 1. Since we're dealing with happiness, it had an exponent of 4. Yeah, that's definitely allometric. You could also think about what's happening in terms of those inputs and outputs. So what do? We doubled our input, but on the other end, our output was getting multiplied by 16. So things are not growing proportional. If things were isometric and we doubled the input, then we'd also just kind of double the output. It wouldn't, things would grow proportionally is what would happen. That power wouldn't magnify things even more. All right, let's see what else we can do with this model, other things we want to know. So we kind of played around with just the models themselves and kind of seeing the relationships between input and output. But if we were to plot the relationship between h and a on a log-log graph, then what exactly would be the slope and the intercept of that brand new line that gets created? So you can see in this question, this is what I was talking about. If they want you to do something on a log-log graph, they'll tell you. If they want it on the original x and y, they won't even mention probably the log-log. There should be some sort of clue if they want you to use logarithms. So yeah, we wanted to take this relationship, put it on a log-log graph, and see what the new slope and y-intercept are going to turn into. Which means we have to start off with our original model and see what we got. So we have happiness, and this was equal to 3 times our mystery parameter to the 4th power. So if it's going to be put on a log-log graph, then I need to take the natural log of both sides. So natural log of the left and the natural log of the right. Okay, now in terms of rules of logarithms, there's only a couple that we need to use. We're going to split things up according to multiplication. Any powers are going to come down in front. Let's see what we got. So let's see, the first one, we'll take our natural log, it will split up. So I'm using this one because the 3 is being multiplied by the 8 to the 4th power. And then we see we have that power of 4, so that's going to come down right in front, ultimately giving us that we have the natural log of h is equal to, I have the natural log of 3, and then 4, the natural log of a. So this is going to be a line. In our log-log space, though, we're going to have some brand new variables. So you're going to go through a renaming convention. Think of this natural log of h, our happiness. We could call this a brand new variable. We'll call this h star. The natural log of 3, this is really going to be our new intercept. I'm going to call this b star. The 4 here, that is going to be our slope. And we'll go ahead and call that one a star. Yeah, and then we can go ahead and answer this question. So specifically, we were after two things. What is the slope and what is the intercept, like the y-intercept, of this brand new line? All right, so we know the slope. Brand new slope is going to be 4. And the intercept, that's our b star. This is going to come from that natural log of 3. So the original, if you were to look at the original, let's see, I'm going to draw just a really rough sketch of both of these. In the original one, the original shape, you would get this really steep curve. But after you're done doing this log-log graph, you'd get a nice straight line. Furthermore, you could graph it out pretty easily because you would know where the intercept is and you would have a good sense of the slope. All right, thoughts or questions on that part? Excellent, good to hear. Let's do one more part to this one. So the last part of this is really interesting. It says that the logarithm of h is an affine linear function of the logarithm of m. If we were to plot the natural log of h on a vertical axis and the natural log of m on a horizontal axis, what would be the slope and the intercept of the resulting line? So there's a lot to kind of unpackage what exactly we're doing with this equation, and then of course a little bit of work to do. So it's kind of giving us a clue that there is some sort of connection between two different variables. Not necessarily the original variables, but there is a connection between the natural log of happiness and the natural log of motivation. And furthermore, that the connection, the relationship that puts these two things together is going to be a linear function. The question is, if we were to plot this, what would be its intercept? What would be its slope? We need to figure out what that connection is if we're actually going to find that later information. Now, if we think about our two models that we have, they're both in terms of some sort of mystery parameter. We don't actually have a model right now that connects happiness to motivation directly. So part of the work will be coming up with a new model that connects those two things, and then we'll get into playing with the natural log to see if we can find that linear relationship that actually connects them. First of all, any thoughts or ideas how we're going to get happiness and motivation connected? Again, if you have any guesses or thoughts, let me know. Put them in the chat box. Not a bad idea, not a bad idea, Arvin. One suggestion is to just take the two and set them equal to each other. You're kind of along the right direction. We will have to set something equal to each other. It's going to come from that mystery parameter. Since both of them involve this mystery A component, then we can actually use that as a link to put happiness and motivation actually connected. Let me go ahead and start writing out my thoughts, and then we'll go from there. So in terms of our happiness model, we know that happiness is equal to 3 times our mystery parameter to the 4th power. And for motivation, this was 1/2 mystery parameter squared. So if you wanted, you could take one of these and really just solve it directly for that mystery parameter A. I'm going to do this with the second one. So if I want to work on getting A all by itself, I could multiply both sides by 2. And then I could ultimately take the square root of both sides. So it's still the second model in a way, but it just has that A, the mystery A kind of isolated. So I can now take that and substitute it into my happiness model. So that's going into my first equation. So h is equal to 3. And instead of a, I'm going to write the square root of 2m. And this will be raised to the 4th power. All right, now we actually have something that will connect our happiness to motivation. H is equal to some version of m. We just want to clean it up a little bit, maybe get rid of those additional square roots. So let's see, the square root raised to the 4th power, this will give me a 2 squared. And the square root of m to the 4th power, that'd be an m squared. So ultimately, this would be h equals 3 times 2 squared. So what is that, 12 times m squared. And there we go. Now we have a brand new model that really just connects our happiness to motivation. We connected these using our mystery parameter A. All right, remember, we're not done yet. The original question, what it's really asking for, is it wants to know more about the linear relationship between two different quantities. Not necessarily the original h and m, but the natural log of h and the natural log of m. Notice it's using those key words. You know, it's telling you about the natural log or the logarithm of these parameters, which is our clue that, yeah, we're going to transform this to a log-log scale. That's really, you want to do the same thing. You want to look for those small key words in there that say, oh yeah, we need to start transforming this thing fast. All right, I have a little bit of space. I think we can do that just fine. So I'm going to take the natural log of the left side, and then we'll take the natural log of the right side. All right, we've seen this play out a couple of times. I'm going to split up the logarithm into two logs that are being added, and then we'll bring down that power. Ultimately, it'll look something like this. So now we have a connection between the natural log of h, this is what I'm going to call h star, and we have a connection to the natural log of m, this is what I'm calling m star. And sure enough, it is a linear function. Now that we have our nice linear function, we can really answer those questions. What's the slope? What's the y-intercept? Can you see them in here? If you think you have them, go ahead and type them in the chat box. What's the slope? What's the y-intercept? What are these two quantities that we're looking for? Bingo, I love it. Yes, you are on the right track. There's our slope. We have a slope of 2. And this entire thing is our intercept. Be careful not to take just the 12. The intercept is the natural log of 12. It's the entire thing. All right, so how are we doing so far? Did we learn some new things about modeling in general, or how to deal with these various different scales? How are we feeling so far? All right, welcome back. Hopefully you had a really nice break. I know I did. I replaced my tea with some good old water. I think I'm good to go for the next second half of this. I answered a couple of questions in the break. As always, if you have other questions, just let me know, and we'll take care of them one at a time. All right, so I think this is a really good part to this next lesson here. We can learn about recursive modeling. I think this is a really fun place to be because actually it's related to memes. One of my favorite memes that you can find on the internet have to deal with recursive, or the idea of recursion. In your free time, if you just want to look up recursion memes, it's a kind of a fun play on learning what recursion really is, and of course just seeing some funny applications of it. But anyway, do that on your own time. It's a lot of fun to look those up. I think that's why I like this subject. Anyway, we want to know, what does it mean to be a recursive model? We'll look at some examples and then look at a simple versus a complex recursive model, and of course what we can do with these things. So a model in general, we're really just trying to model some sort of real phenomenon out in the world, and doing so using some sort of equation. In a recursive model, these are a very special type of equation. Essentially what we're doing is we're trying to define what's happening in the next generation in terms of a previous generation. So whatever's happening is immediately affected by what happened directly before it. Because it has this, what is this effect, then they take on a very special form. You'll notice that there's a lot of subscripts with this notation here, but it's really trying to get across that concept of that what's happening in this new generation is affected by the things that came before it. So in this case, I'm using U to maybe stand for a population, and the T in this case is some sort of time parameter. So in the very next year, or the next time, I'm going to say the next generation, you'll see that that is some sort of equation that has inputs of the previous generations. So there's t minus 1, there's t minus 2. They could go all the way down to let's say u of 0. I'm just going to say previous generations. And there also could be some constants in there. Constant. All right. Like before, these equations don't actually need to look complicated. It all just kind of depends on what you're modeling. So we'll look at 3 different types of situations and the recursive model for each of these sets. A good famous one of these is what is known as the Fibonacci sequence. So this is the sequence that goes 1, 1, then 2, then 3, then 5, then 8. It's usually introduced to, I don't know, people in school as just a way of kind of picking out patterns. And of course, the way this pattern is described is, if I want the next term in this sequence, I'd simply look at the 2 before it and add them together. So I only took this out to 8, but if I wanted to go one further, let's see, what would the next one be? The next one would have to be 13, because that would be 5 plus 8. Let's see, the next one after that would be 21. That'd be 8 plus 13. And the one after that would be 34. I could continue this as far as I wanted. So if I really want to describe this using a recursive equation, then I'm going to use those subscripts. So this UT would essentially say, no matter where you are in this list, how would you need to build this number? Well, I need to look at the 2 previous ones. So at t minus 1 and t minus 2, I would need to add those together to get the brand new one. Now, by itself, that equation doesn't necessarily describe the entire Fibonacci sequence. It just tells you like a rule of how to generate new numbers. We also need a seed or some sort of starting place to get the process going. And that's what these other 2 parts are. So it has to give us 2 numbers, let's say the 1 and the 1, to start this process. If I start off with 2 different numbers, like 1 and 3 or 1 and 4, I would get a different sequence, but I could still keep the same rule. And then this would be a really good first example of something that's recursive. Let's check out another one. This one is actually a really big one when it comes to probability or various different types of statistics. This is what is known as a factorial. So this is for taking care of numbers like, let's say 5 factorial. The way this works is you start at the number, let's say 5, and you multiply it by 1 less every single time. So this would be 5 times 4 times 3 times 2 times 1. And then you could just multiply all those together and see what you get. In general, you could come up with a nice, good recursive formula for this. This is because 5 factorial is really equal to 5 multiplied by 4 factorial. So this is a way of saying, well, if I want to know the value of 5 factorial, then I can essentially look at what my answer was for the previous generation, 4 factorial, and I'll just multiply that by the number I'm at, by 5, which is exactly what this rule is saying. I want to look at UN, but I'll do that by looking at my previous result, UN minus 1. We'll just multiply it by n wherever I'm at. If I want the specific, let's say, factorial notation that we're familiar with, this will also need some sort of starting place. This one starts with the first number being 1. All right, let's do one more of these. This is kind of a famous one if you're modeling populations or anything like that. This would be the population of bunnies. So I'm looking at the numbers here. We have 2 bunnies, and then we have 4, and then we have 8, and then we have 16, and then we have 32. And so you can look at this pattern and maybe figure out what's going on here. So far, it looks like things are doubling every single time. So we started with 2, but then it doubled to 4, doubled to 8, we're up to 16. And we'd really consider that pattern, really continuing from there. So in terms of my model, I would say that every brand new generation would be twice the previous one, or 2 times u to the t. Our initial seed, the starting point for all of this, would be 2, and then we'd be good to go. So all of these are really examples of really just describing what's happening using a recursive model. You want to take note, though, that it's not the only way that you can describe the end result. In this particular example, yes, you can describe it recursively, but you can also describe it in a more explicit form or in a more direct form. That more direct form would say, well, if I want to know about some sort of number even further out down on this list, and I don't want to always have to compute the one right before it, then I could just look at what number I started with and multiply that by 2 to some sort of power. Kind of the fun part about dealing with these recursive models is that, yes, we can describe them recursively, but there also could be a more direct version, a more explicit version that could also kind of jump us farther down that line without having to do all the previous ones. And this is really the idea of kind of looking at the difference between a recursive model versus an explicit model. In general, we have two different forms, and they look like this. So here for our recursive model, these are the ones we've just been covering. Remember, you're looking at what the newest generation is going to be in terms of all of those older generations. In order to get things started, you will usually need some sort of initial value to start things off, but it's going to always be defined using some previous terms. If you're dealing with an explicit model, these are a little bit more powerful in some sense. Then really the only parameters you'll need are maybe how many generations down you are, some sort of function of t, and you'll need to know where you started. You don't necessarily need to know about any previous generations. So that's why you're not seeing information like u of t minus 1 or u of t minus 2. You simply don't need those. And if you want maybe two quick examples, you can definitely see it for the ones we did. So for our population of bunnies, we would know that this is a recursive model because the new generation is being described using some sort of previous generation. I guess I should put the seed in there or where it starts. Whereas this other model, let's say u of t equals 2t times u0, this would definitely be an explicit form because it doesn't have a t minus 1. The only u that's being really described here is that first initial u. Everything else is really just in terms of time. Thoughts or questions about the difference between a recursive model versus an explicit model? Most of the questions that deal with these two types, if you're kind of thinking ahead, will usually deal with, let's say, populations or investments, stuff like that. Oh, excellent question. This is the one where you're looking at that explicit model and you're like, wait a minute, where'd they get that 2 to the t power? One way that you could get that t component of it is to actually look at the pattern of this, okay? Let's go back up to where those numbers were, right? I think we can see them, yeah. So here I'm starting at 2, and I can see that the next number is going to be 2 times 2. Here, this is going to be 4 times 2. And then eventually we'll have 8 times 2. So it's really just looking at the same numbers, but saying, all right, what did I have to multiply my original amount by, the 2, in order to get to this brand new number? And so you're multiplying by 2, you're multiplying by 4, then 8, and then 16. Essentially what's happening there is you're getting some sort of power of 2. That's one way to do it, but it's not the only way to do it. The other way to do it is to start off with that recursive model and then slowly build it into an explicit form. We will go ahead and do that because it is actually part of really understanding the connection between these two things. I think that'll actually really help you figure out where that 2 is coming from. All right, let's dive into the details, okay? So this population about bunnies is really a good example of what we would call a simple recursive model. In a simple recursive model, you can build an explicit form by really starting off with that simple model and just kind of reusing it over and over again. Keep in mind that with a simple recursive model, something that you're trying to model like the population or something like that, it really does follow this particular form here. So let me highlight it. So you're looking at a new generation being based off of the previous generation, possibly multiplied by some sort of constant b. That constant b is really just representing maybe a percentage or some sort of growth rate or decay rate in the population itself. For example, in that bunny example, every new generation was twice as much, so the growth rate for b would be 2. Let's see, what else do I want to say about this one? If it was some sort of decay rate, I don't know, something where the population was going down, then that value of b would be less than 1 so that you're multiplying and making it smaller. In order to turn this into a explicit form, we essentially just need to iterate this thing over and over again until we essentially stack up those extra terms of b. So I've highlighted what the explicit form will turn into, and you can see how this worked out for our bunny example. So we start off with ut plus 1 is equal to 2 ut, and the explicit form was 2 to the t. So really taking that growth rate, 2 to the t multiplied by u sub 0. Let's see where that 2 even comes from. How does that work out? So imagine starting off with one of these simple models. And you'll see what happens is we'll start to stack up those b components. That's really what happens here. So if I started at, let's say, time 0, and I was trying to figure out the next generation, I really wanted to figure out what was happening with U1. Well, I could go back up to my rule and say, well, this is based off of b times the previous generation. So b times u sub 0. So that would be a good expression for what's happening for u sub 1. If I wanted to go out to the next generation, let's say u sub 2, then I'd do it pretty much the same way. I'd say, all right, that's multiplied by b times the previous generation. But then I could go back and I could actually substitute in that previous generation. So that'd be b. The previous generation would be b times u sub 0. So we're getting this b squared times u sub 0. Okay, so if I wanted to do yet another generation, you can see there's definitely going to be a pattern to this. So I'm going to look at what the previous one was. We're going to multiply it by b. But we've already done a little bit of work knowing what the previous one even is. So you can see that it has these extra b's that really just start accumulating and stacking up. In fact, we can probably get into a little bit of a shortcut here. If I wanted to get all the way up to u sub 4, the fourth generation, of course, this is going to be b to the fourth power, u sub 0. So that's how essentially you build that explicit form, that, all right, if I did this, and I was curious about looking at the t generation much farther down the line, then whatever my growth factor is, this b would need to be raised to the t power. And of course, it'd also depend on where I start. Does that help you figure out maybe where we're getting that 2 to the t power in there? Excellent to hear. Yes, yes. We will play around with this idea. That way we make it even more solid. Let's go ahead and try an example and see what we can do, okay? So as I mentioned, these problems are usually based around population or investments. Really good place to kind of play around with this simple recursive model. So in this one, we have an initial investment of about $1,000, and it's going to grow in value by 10% every single year. We want to first just create a recursive model that represents the situation, and then we'll see what questions we can answer about it once we actually have that model on the page. Okay, so our clues for this one is it's kind of giving us a hint here. It says we want a recursive model. So in your mind, think, yes, I want to say what the new generation is going to look like based off of previous generations. Other clues we have in here, we know what the starting amount is, and we have a sense of how much it is going to grow. So I'm going to initially label the $1,000. That would be our starting amount. I'm going to call that u sub 0. Yeah, let's see if we can build this recursive part. So every new generation that we come up with, so u of t plus 1, this is going to grow by 10% every single year. So I can think of this as 0.1 multiplied by the previous year's amount. And I'm also going to add in whatever the previous amount is, because with money, it's always like 10% based off of what you had last year, plus you still have what you had last year. Now, both of these involve this ut piece, so I might as well combine those together. So 1.1 u of t. And now we have our model. So one part is the rule that says how is it going to grow from generation to generation, and the other part really just tells us where we're going to start. We're going to start with $1,000. And sure enough, if you play around with this, you can see that in the next year, you're going to have $1,100. This growth rate is more than 1, so things are really growing over time. Excellent. All right, the next part of this really says, well, what is the explicit solution for this recursive model? So we have a nice recursive model. It's based off of previous generations. But if I want to jump down to the 100th year, I don't necessarily want to use this as a model, just because I'd have to do it like 100 times in a row to figure out what's happening in that 100th year. With an explicit model, we can just jump to 100 and get it. So what would this model even look like? Well, if we identify what our B value is, then we can actually just write down that explicit form. So UT, for whatever year we can think of, would be 1.1 raised to the T power. And then we have our initial amount. This would be multiplied by 1,000. And there we go. That would be our explicit model, or explicit solution for our recursive model. Okay, so we have two different ways of describing the same situation. Let's think carefully when we get to part C here. Part C says, when will the investment be worth more than double the original amount? So we have two equations that we can work with. We have a recursive one, we have an explicit one. If we're going to answer this question, what do you think would be more useful to work with? Go ahead and take a guess, put it in the chat box right now. Would you rather work with the recursive one, or would you rather work with the explicit one? Which one's going to be more advantageous? Yes, those are excellent. I see a hand up in the chat box here. Do you want to be allowed to talk? Okay, just making sure, yes, I agree. You would want to use the explicit form. Yeah, that way we could just solve for the time directly. Let's go ahead and do it. So in the explicit form, we know that, what is it? UT, this is going to equal our 1.1t, and we're starting off with $1,000. So I want to know when this thing is going to be more than double. So if I just solve this when it will be exactly doubled, I know that the time will be some point beyond whatever time we solve. Okay, so now we just need to get the t all by itself. All right, let's see what we can do. I'm going to solve this by dividing both sides by 1,000. And then we really need to get that t outside of the power. So this is where logarithms come into play. Logarithms really are the perfect tool for any time you have something in the power and you want to bring them down out of the power. In this case, we really want that t no longer in the top there. So this will help out a bunch. Okay, that's looking pretty good. T is almost all by itself. Now we just need to divide both sides by the natural log of 1.1. And we are good. So I'm looking at the natural log of 2, all divided by the natural log of 1.1, and this will equal t. All right, let me grab my calculator here real quick. What is that? Natural log of 2 divided by natural log of 1.1. Excellent. So I'm getting 7.27-ish for t. We can say about 7.3. I think these are in years. Yes. So yes, you want to use the explicit model. That's something that you can solve for time directly, and you're good to go. Questions or thoughts about this particular simple model? All right, let's go ahead and try another one of these. I think I'm going to turn this one over to you a little bit. This one says we have the half-life of a substance, and that half-life happens to be 60 years. So what that means is, after 60 years, we will have exactly half as much as what you started with. Now, suppose that we're starting with 500 grams of this substance. We want to do a lot of the similar things. First, we want to write down a model that really connects our time to how much we're going to end up with. And then once we have that model on the page, we're going to see if we can figure out, when we'll have less than 100 grams. So take a few moments, see if you could first develop what the model's even going to look like. Also keep in mind that what I'm assuming here is really that simple recursive model. So this is kind of a weird substance. Like every year it's going to change by some amount. It's not going to be like, what do I want to say? It's not like some weird radioactive substance. Um, Almost maybe think of it as a population. Like the population after 60 years is going to be exactly half as what we started with. Good question. This question says, if I start off with a recursive model and I'm turning it into an explicit model, do we do the b to the t times the initial value? Is that really the form for our explicit? And the answer is yes. So if you want to write these both on the same page, might be a good way to keep them both straight. So in the recursive version, we have b multiplied by our previous generation. I'm going to label that one recursive. We'd also want to know where this starts versus the explicit form. Oops. Where that one's only based off of what the growth rate is to some sort of power of t and where you start. Forgot to label that one explicit. Nice. All right, so let's see what we can do with this one. This one, we have information about the half-life, but they never really give us any direct information about how much it's changing from generation to generation. So if I'm looking at both of these models and I'm like, well, which one should I start to try and write down? I'm kind of leaning more towards the explicit model. Why am I doing that? Because I know how much we start with. We're starting with 500 grams. And I know when it will be half of that, when the half-life is. But again, what I'm missing, the reason why I'm not going for the recursive model is because I don't know how much is changing from year to year. Okay, so let's do that. Let's start off with this explicit form and see how we can use that to actually find the value of B. So I know that after 60 years, we'll have half of the substance. So if we start off with 500, we should end up with 250 grams. That's not a generic T, that should be 60 years. So I'm going to put a little 60 there. Okay, that looks pretty good. We can now take this and solve it directly for B. So I'm just going to divide both sides by 500. So that'd be 1/2 is equal to B to the power of 60. I could use natural logs if I wanted to, I don't know, bring down the power, or I could take the 60th root of both sides. That also works out pretty good. So 1/60th, 1/60th. So this is, I'm going to write the 1/2 as 0.5 just so it doesn't mess up my other fraction that I got going on here. Either way, this gives me a value for B. And let's see, how big is this value? So 1/2 to the 1 divided by 60. This value, B, is approximately 0.988 and some change. Okay, but once I actually have a value for B, then I can go ahead and run it and put it back in my model here. So we built this from the explicit one. Seems like a good place to use this. And of course, we started with 500. So here's a nice little model for this situation. All right, now that we actually have a model, of course, we can take this further. We can say, all right, what do we want to do with this? With the model, now we can answer when the amount of the substance will actually be less than 100 grams. So like before, we're still using that explicit form, but now I'm trying to figure out more about the time element. So I can put the 100 grams in for my U of t and then directly solve for t. Furthermore, now that we actually know what B is, we can, it'll end up in the shuffle as well. All right, so let's see. Let's set this up. We want to know when it will be 100 grams. That's fine. We don't know the t yet, so that'll just stay in the power. but it's really the only unknown that we have, so I'm just going to solve this directly for t. Let's see, what can we do with this one? Well, I can divide both sides by 500. So this will give me a 1/5. The t, the part that we're actually looking for, is in the power. So I want to take the natural log of both sides to really bring it down out of that power. So natural log of the left, natural log of the right. So 1/5. So this is 0.5 raised to the power of 1/60th times t. All right, so let's see, both those can be brought out front. Okay, it's looking better and better. The only thing we're after now is just the t. It's being multiplied by all of that other stuff. So I'm going to multiply by 60. I'm going to divide by that natural log. That should shuffle things over to the other side just fine. So 60 multiplied by the natural log of 1/5, all divided by the natural log of 0.5 equals t. All right, time to grab my calculator and see exactly where this ends up. Excellent. So it looks like 139.31, or you could say around 139 years, maybe 140 years if you're rounding up. Excellent. But yeah, we started off with the explicit form directly. It allowed us to directly solve for that t component, and we were good to go. Very nice. Looks like you got the same answer that I did. Always a good sign. It means we're both on the same page, right? All right, questions or thoughts about this simple model? Excellent question. This one says, can I take the natural log of 1/5 and really write that as the natural log of 1 minus the natural log of 5? You can. That's completely okay. That follows our rules of logarithms. And actually, if you play around with it a little bit more, you can write it just as the negative natural log of 5. That's completely okay. But I'm going to write it down here. Actually, no, let's do a different color. I don't want to mess up any of our other good work here. I'm going to write down natural log of 1/5. So that's equal to the natural log of 1 minus the natural log of 5. The natural log of 1 is really just 0. So it just turns into the negative natural log of 5. Scroll down a little bit. Yeah, that's completely fine. This question says, does B always represent growth or decline in terms of the rate? It might actually represent... Oh, I'm sorry. Yes, it is either a growth rate or a decline rate. It's one or the other, or at least the way I'm using B in these ones. Good question. This one says, how did I get a recursive model for part A? Let's scroll up and see exactly what we got going on there. I did not have a recursive model for part A because I didn't really know how it was changing year after year. So that's why we actually started off with the explicit model, so that we could actually figure out what the rate was. Now, the fun part is once you, I guess, start with the explicit model, you go through the work, you find a value for B, you could take that value of B and then build a recursive model for it. So yeah, let's just take the work that we have here. I have B is equal to, what is that, 0.5 to the 1/60th? Yeah, let's build the recursive version of this. So this would be U of t plus 1 equals, and then I'd have the value of B, so 0.5 to the 1/60th. And then this would be multiplied by the previous generation, We'd also want to say where we start, so it needs the 500 to begin. There we go. Now we have our explicit versus our recursive model way of describing, but we needed our value of b to do either one. All right, other thoughts, other questions? Oops, did I miss one? Good deal, good deal. All right, with all of that out of the way, let's go check out the complicated version of this. Well, actually, it's not too much more complicated. It's just known as the complex version of it. But we definitely want to know about this before we are done today. So a slightly more complicated version of this takes into account that maybe we'll also add or subtract some amount from generation to generation. Think of any type of population where you're trying to be a little bit more careful or trying to be a little bit more realistic on how you model it. So maybe in my vegetable garden, yeah, I'm going to end up with, double year over year, but I also give like a certain portion to my neighbor. So there's going to be a harvesting amount every single year. So in this more complex recursive model, we essentially have an additional parameter worked in here. Let's check out the pieces. So here I have this u of t plus 1, so that's the new generation. It is either going to grow or decline by some sort of rate. So in this case, the a is being represented by that growth or decline rate of the previous generation. And then I have this plus b. That's the additional amount that I'm either just going to grow or reduce generation by generation. Here's another example, maybe to connect it to actually finances. Maybe I start off with $1,000 and every year I'll get 10% more off of my original investment, which is great, right? It means every year I'll earn a little bit more. But in addition to that, every year I'm just going to chuck in an extra 50 bucks. So in a model like that, I could say that every new year, I would end up with 10% more than the previous generation, and I'm going to chuck in an extra 50 bucks. So I have this slightly more complicated version because of that additional 50 that we're throwing in. Now, this is the recursive version of this, but you could also build an explicit version, which is really cool. In order to get that more explicit version, it's a little bit more work to do, okay? So essentially the steps for this is to go through a process of finding the equilibrium or the steady state solution of this. That's the place where it's essentially not going to grow from generation to generation. And you're going to use that as a new parameter. So this is where you can kind of rename things and then do a little bit of algebra so that it turns into more of a simple model. Now this will be a simple model in these new variables. And with that simple model, then you could come up with the explicit version using those new variables. Of course, those are for the new variables. You really want it for the original variables. So then you have to go through a process of turning everything back into those old variables. But you can do it. Before we get too far, though, I will write down what the explicit version looks like, and then we'll talk more about how you actually build this thing. So this is actually really cool. So I'm going to write down the general form. This is for the more complex one. So u sub 0 is our starting amount. Actually, I'm going to draw that one a little bit farther away. It says we know it, but it's not part of the same equation. It's more like here's our starting amount. There's our rule of how we get generation to generation. This is our recursive. And now we want the explicit. So this would be u of t is equal to, we have u sub 0 plus, nope, not plus, minus b all divided by 1 minus a to the t, plus b over 1 minus a. Of course, this only works if a, does not equal 1. Just something to keep in mind. And you can see that maybe this is why it's called the complex version of it. The explicit form has got a lot of stuff going on in it. Well, good question. This one says for the simple model for, let's say, the previous question that we were working on, what were the words or terms in the question you highlighted to know to use an explicit model? Oh, yeah, good question. Yeah, for this previous one, I knew that I was going to need an explicit model, not necessarily because of words that were in there, but the words that were missing. There was no information about how it grew from generation to generation. The only information I had was how it started at an original amount of 500 and then just jumped to half of that 60 years later. So there was a huge gap. If you had information from generation to generation, it really lent it more to a recursive model. That's why we went explicit in that one. All right, so we have our recursive version, we have the explicit version. Let's go through a process of building an explicit version so you see how this works. It's actually not as bad as it looks, but we can do it, okay? And the way I'm going to do this in the booklet is we're just going to take this step by step with some actual numbers. So here I'm starting off with a recursive version where I actually know that the rate is going to be 1.5, so things are going up by 50%. And I know that we have some sort of starting amount of, let's say, 20, but also every generation we're going to be adding in an additional 100. So that's the way I'm kind of decoding our current recursive equation that we have here. With these current parameters, you could take the formula that I just wrote down and build an explicit form. You just have to identify your A and your B in here. You could do it. So A in this case is going to be that 1.5. B is going to be that 100. And yeah, the A sub 0, yeah, that's what we already identified as our starting amount. That looks good. So we could just build it directly. We could say U of t is equal to, let's go ahead and copy that down. So I'd start off with the U sub 0 minus, so that'd be 20 minus. Then I'd want to take my B value, so that's 100, divided by 1 minus A, so 1.5. That was good. Then I'd take A, 1.5 to the power of t, plus 100 all over 1 minus 1.5. Okay, so I'm really just identifying my A and B, plugging it directly into the explicit version, and then you'd go through a process of simplifying this. I'll save you some time of multiplying those terms together and actually going through that simplifying process. This turns into 220 multiplied by 1.5 to the power of t minus 200. I'm going to box that in there. That would be the explicit version. Yeah, okay. So if you have the formula for the explicit version and you just want to jump to that explicit form, not a bad idea. Definitely write it down somewhere if you already haven't done so, because you want to be able to do that to save yourself some time. We will go through the process of how you can get it the long way, how you could build it. And what you're going to get from that is you don't always want to have to build it. You want to be able to use this formula to just kind of jump to that explicit version a lot quicker. All right, let's give this a try. Let's go through the building process and see what happens. Let's see how I even came up with this and go from there. Okay, so the idea is to start off by finding the steady state solution or the equilibrium. This is really the point where the generations are not going to change. So this is where U of t plus 1 minus U of t, so the new generation minus the previous generation, is going to equal 0, no change. So we want to solve this. And I'm going to put in information from our recursive formula to figure out what the value would even need to be. So ut plus 1, well, that's 1.5 u of t plus 100. So I've really just replaced that initial term. Now I'm going to combine things. I want to solve for u sub t. So let's see, combining my u sub t's, this would be 0.5 u sub t. I could move the 100 to the other side. Now simply divide by 1/2. So I get negative 200. So if my population was, I don't know, negative 200, that would be the one place where things aren't really changing. It may not make sense in the context of the problem itself, but it is a number that will help us figure out a more explicit solution for this. Anyway, this is the value that we're looking for. This is what I'm going to call U star. All right, now that we have this U star, this steady state, we're going to use it to develop a brand new variable. This is what I'm going to call x sub t. So x sub t is going to be based off of our original variable, these u's, minus this value of u star. So in this case, things are really just going to be shifted over a little bit. So what's my value for ut? Let's see. And let's see, minus my minus 200. So x sub t would have to equal u sub t plus 200. I could also do this for my x sub 0. This would really be u sub 0 minus that u star. So in a similar way, this is just my initial amount plus the 200. Circle both of those. Excellent. So now we have a new variable. This is what we're calling u. Oh, good question. This one says, how did I know that u sub t minus 1 was 1.5t plus 100? How did I end up subbing that out? This was given in our original recursive formula. So I'm essentially looking at that recursive formula and putting in that information. It's kind of like what we did last time. We're like starting off with the recursive version so we can build into the more explicit version. All right, we have a new variable. We have these x's running around. Now we need to build a recursive version using this brand new variable. So this is where we build x sub t plus 1. So x sub t plus 1. Well, this will be based off of u, t plus 1, minus our u star. All right, now we have formulas for both of these, so I'm going to substitute them in. So this again comes from our recursive formula, so 1.5 ut. This is plus 100. We know the value of u star is minus 200, so minus minus a 200 turns into plus 200. And we actually have a formula for u sub t in terms of x sub t. So if we wanted to swap that out, we could as well. So I'm going to do that. So 1.5, it's just a plus 300 on the end. So this would be x sub t minus 200. So I'm taking this, plugging it right into there. And now we can start to combine some of our terms. So let's see, what is 1.5 multiplied by 200? Well, that's minus 300. So we get 1.5 x sub t minus 300 plus 300. We're seeing that those 300s cancel each other out. And sure enough, in this brand new variable, this x variable that we came up with, now we have a recursive version of it, but it's a simple recursive version of it. It's not our complex model. It's just some sort of a parameter. In this case, 1.5 multiplied the previous generation. Ooh, let's do that in green. This is now the simple version. Smiley. So all of that work is really just to get a brand new variable in here, get it to where it is a simple model using this brand new variable. And now I can write down the explicit version of the simple model. So let's see, what's the explicit version? Well, any new generation will be the growth parameter raised to the power of t, some initial amount. Okay, that looks excellent. But of course, we want our original variable in there. We don't want to deal with x's. So now I could go through my formula that we just built here, replace all of these x's with their appropriate u versions. So you do have to scroll back up and be like, well, what were these equal to? But you can see they're just up here. So I have a version for x sub t, I have a version for x sub 0. I can just substitute those in directly. So this would be u sub t plus 200 equals 1.5 to the t. And this is u sub 0 plus 200. Oh, I forgot something. Why did I do that? I forgot that I have my x sub 0 that I could go ahead and replace that. Let's go ahead and do that real quick. 1.5 t, because the starting amount would be the x sub 0. Yeah. It's u sub 0 plus the 200. And we know that the starting amount for u sub 0 is 20. So 20 plus 200. There we go. 1.5 t, 220. There we are. And now we can rewrite that using the brand new variable. I like it. So u sub t plus 200 equals 1.5 t times 220. Moving the 200 to the other side. And there we go. That would be our explicit form. All right, so lessons to take away from this. If you have the recursive form, can you build using algebra into the explicit form? The answer is yes, we just did it. Do you always want to have to do this? The answer is no, you don't always want to have to fight through that. That's a lot of work. That's why you want to be able to use this formula right here, so you can just jump to it if you really want to. So you don't have to go through all of that algebra. Excellent, excellent. All right, looks like we are almost done for today. So I just want to do a couple of more things before we are done. Just some simple things. Notice how we covered two different types of recursion models. We had a simple one and a complex one. Really the only difference of these is that it had, in the complex one, some sort of additional parameter where we were adding or subtracting amount every single generation. The A in both of these models is going to really represent either a growth rate or a decay rate, depending on how big it is. Think of the value of B, that extra parameter is really like a withdrawal or harvest rate. It's adding a fixed amount every single generation. Right, there are more examples left in the book that we unfortunately just don't have time to get to, but definitely try them out. There is a solution manual that is going to be posted with this. So I really recommend trying these out and then running back, checking to see how you did on them. You have all of the information you need to actually do very well on these example problems. Let's see, other things that I want to mention. Oh, we got some questions that have popped up here. This question says, I was wondering if the WISE subscription, our study pass, does that cover the weekly prep courses? Those are two different products, so unfortunately they do not cover each other. If you get the WISE study pass, that does not count towards these weekly prep sessions. Let's see, what else do I got here? This one says, is the recording for this session provided if we are watching on a free trial? I believe actually the free trial recordings are posted just so that people have an idea of what the future sessions are going to look like. So I think the first two sessions actually are free. So this week and next week are going to be free. So yeah, you should be able to find those recordings just fine. I think the future ones though are not recorded or saved. All right, other last quick things I want to mention. Of course, the success of these weekly sessions is partially based off of how many people are interested in them. So if you had a lot of fun today, if you learned something new, definitely tell your friends, tell other people in your class. I'd love to see some more friendly faces here, and we could go over even more material.